and gentlemen, a very warm welcome to you all. Michael Lloyd is otherwise detained. He'd of course much rather being here, but it's my privilege to be the person to introduce Jessica Pointing, who's our principal now, or vice principal now, lecturer this morning, on the topic of quantum computing. We're very excited about this. That's an astonishing CV. I won't embarrass her with the entire list, but a few edited highlights. She's been a researcher at Stanford, Harvard, and MIT. So three of the top places in the States, in case you didn't already know. Doing her DPhil now in quantum computing at St. Peter's College. She was an intern at Google. So if you've seen The Intern, you know how competitive that is. No small feat. IBM Q Quantum Computer Awards, Forbes 30 for under 30s science category. Remarkable, gifted scientist who's going to come and talk to us about quantum computing. So over to you, Jessica.
Thank you. Can you all hear me?
Yeah.
So in this video, I'm pouring liquid nitrogen in the Department of Physics, which isn't too far from here. And I also have here a superconductor. And here is a track of rare earth magnets. Now something special happens when I dip the superconductor into liquid nitrogen. And when I place it on top of the magnetic track, it levitates. Imagine what you could do with this technology. Perhaps you could create a hovering train, getting you to your destination faster, using less energy. Some people have actually used it to create a hovering skateboard, like in Back to the Future. There are many potential applications of this technology, from storing energy to power cables. But the problem is it's difficult to implement in real life. Why? Well, one of the reasons is because you need to cool down this superconductor to minus 181 degrees Celsius. But imagine if we could create a superconductor that doesn't need to be cooled down, that could work at normal temperatures and pressures. Well, this might be possible if we could understand how the atoms in this superconductor behave. But the problem is that the world's best computer does not have the power to understand this. Well, a quantum computer could change that, because a quantum computer is a fundamentally new type of computer that uses quantum physics. Everything in this world is made up of atoms, and quantum physics describes how those atoms behave. Therefore, we could potentially understand how the atoms in this superconductor behave, and that could give us insight into creating a superconductor that could work at normal temperatures and pressures. Therefore, quantum computing could potentially unlock the amazing applications of this superconductor technology. The first time that I saw this experiment was when I was a young girl in middle school. I remember going to this event at the Microsoft offices in Reading, and this is actually a picture from the actual event more than 10 years ago. And I remember walking into this room, and there were all sorts of crazy experiments on display. There was the liquid nitrogen and explosions. And I remember the speaker, Chris Bishop, the one in the green shirt, describing quantum physics. And it blew my mind. And that was sort of the spark that led me to study physics and computer science at university. And when I got to university, I started several quantum computing associations, such as the Harvard College Quantum Computing Association and the Stanford one. And now I'm doing my DPhil here, specializing in quantum computing. And over the years, from the time that this picture was taken until now, I've seen that quantum computing, and I believe that quantum computing could transform our world. So why? And that's what we're going to explore in this talk. One is because of the potential of quantum computing. Two is because of the power of quantum computing. And three is because of the progress of significant achievements that we've already made. So first off, let's understand, what could a quantum computer do that a normal computer can't do? I've already illustrated one example, but let's take a look at some more. So one is searching and factoring. So actually, to illustrate this example, I have two bags. So this is going to be an unstructured search example. So let's say in this bag, I have 4 balls, and I do. I have 3 of them are white, 1, 2, 3, and one of them is blue. So let's say I'm searching for the blue ball, and I put them all inside the bag, I close it, shake it up, and I can't look inside. So I basically have to pick out a ball, check whether it's blue, and then continue until I find the blue ball. Yeah, very impressive. So, as you can see, this is sort of what a classical computer would do. So, classical computers are basically our normal computers. So, if you had 4 balls, it would take up to 4 tries, right? Because I might have gone with the blue ball on the last try. But what if this were a quantum computer? Well, even if all 4 balls are inside the bag, let's say this is the quantum computer, I can actually get the blue ball on the first try. Guaranteed. But actually, with a quantum computer, you can get it in 1 try every single time if you're searching for the blue ball. So essentially, this problem has been sped up from 4 tries to 1 try. And in fact, you can generalize this. Let's say you had n balls, or let's say n entries in a database. On a quantum computer, you can search for a particular entry up to square root of n. So you sped up that process. So how do we know this is possible? Well, this is because researchers have come up with quantum algorithms. So a quantum algorithm is basically a set of instructions that you give to the quantum computer. And there's this guy called Grover who came up with this algorithm. So it's called Grover's algorithm. And he found out that quantum computing can speed up unstructured search. And quantum computing can speed up other processes as well. So, for example, let's say I give your computer the number 15, and I say, what 2 numbers must you multiply to give 15? Of course, that's extremely easy. Your computer will say 5 and 3. But what happens if I give it this 617-digit number, and now I say, find me 2 numbers you must multiply to give me this? Well, that's going to be pretty hard. In fact, your computer's going to have a hard time solving this. It might just blow up. Because it's estimated it could take up to 1 billion years using the best known algorithms just to find out what those 2 numbers are. But what about a quantum computer? How long do you think it could take? And actually, I have a poll, so I want to see how long you think it could take. And let's see what you guys know. So, if you go to pollab.com/quantum225, or you can text the number, you can put in your answer. So I'll give you guys maybe about a few seconds to put in an answer. So how long do you think it could take a quantum computer to find out what those 2 numbers are? So let's see if we are getting some responses. Okay, now we're getting responses. Great. Okay, cool. So, alright, you guys are very optimistic. Okay. Alright, now we're getting some non-optimistic. Well, still pretty optimistic, right? Okay, great. So, the correct answer is 100 seconds. So, but that's pretty crazy, right? From literally a billion years to 100 seconds. So as you can see, a quantum computer can speed up problems, some certain problems, exponentially. And in fact, this is possible because of another quantum algorithm called Shor's algorithm. And actually, Peter Shor, he's a professor at MIT, and he created this algorithm. Now, this is a very important problem because if you're familiar with encryption, those 2 numbers are basically kind of what keeps all of our data secure on the internet. Because you can think all of your data is encrypted by this lock, and as long as you don't have those 2 numbers, which are equivalent to the key, you can't decrypt someone's data. But with a quantum computer, because we could have those 2 numbers, we could actually essentially unlock the lock and basically decrypt data. And that's a big problem, and that's actually one of the biggest sort of threats of quantum computing, is because it could, like for example, your credit card information or sensitive government information is all encrypted to protect it from hackers and people who want to use it for bad purposes. So if a quantum computer could unlock that, that is a potential problem. But there's several things you need to know. One is we don't actually have a quantum computer that's powerful enough to do that yet, and it's estimated it could take about 10 years to get there. And second is people are coming up with something called post-quantum cryptography. So these are methods that could be potentially safe against quantum computers, but But this is still an active area of research, and people are actively thinking about this. So we've seen sort of these very specific algorithms, searching and factoring, and I want to look at a second potential class of algorithms, of applications, and this is understanding nature. So basically everything, as I said, is made up of atoms, and they all follow the laws of quantum physics. So it makes sense that we'd want to use a quantum system, which a quantum computer is, to simulate and understand another quantum system, which nature is. And this has a lot of applications. So for example, in medicine, you want to create medicines that interact with the molecules in your body to cure some sort of problem. Well, with a quantum computer, we could potentially simulate those molecules to help us design new types of medicine. Or how about a vaccine? We're all familiar now with the time frame it's taken to find a vaccine. A quantum computer could potentially help us find vaccines faster. Or how about material science? Again, you want to create new molecules, new materials, such that your laptop, your phone is lighter, stronger, and has the properties that you want. Well, a quantum computer could potentially help that. And then third, which is probably more relevant to this series, is machine learning and AI. And just as we've had the computers we have now have really advanced artificial intelligence, because we had algorithms before, but we didn't have powerful enough computers to actually be able to run them. Well, maybe in a similar way, a quantum computer could help advance AI. And this may sound like a lot of buzzwords, quantum machine learning, but it is actually a field that people are working on, and if you understand the mathematics of machine learning, it's linear algebra, vectors, matrices. Quantum computing is actually very similar, so you can map the two together mathematically. So here are three potential applications from searching and factoring to understanding nature to machine learning. So now you might be asking, why can quantum computing do this? What is the power of it? And but basically, as you can see, it makes things that are practically impossible today to be made possible. And that's why it has a whole variety of applications in AI, medicine, finance, space, logistics, because the problems it can solve are quite broad enough that it could be applied to all of these different industries. So we could potentially solve today's unsolved problems with quantum computers. So now let's take a look at the power of quantum computing and why it can actually do this. So first we need to understand the fundamental building block of the quantum computer, which is the quantum bit. So in order to understand this, let's say you're typing up an email to your friend, you say, hey, smiley face. Well, what is your computer doing? Well, you may speak English, but your computer speaks a language of binary. So anything that you type is basically translated to a sequence of zeros and ones. So H-E-Y, smiley face, is translated to the specific sequence of zeros and ones. So this is called the bit, the 0 or 1. And to illustrate this bit, I actually have this donut. So let's say the frosted side is equivalent to 1, and the plain side is equivalent to 0. So this is a classical bit. It can either be 0 or 1. But what about a quantum computer? Very creatively, they're called quantum bits. So a quantum bit can actually also be 0, and it can be 1. But it has something special. It has access to quantum physics, which means it can behave in a quantum way. So in particular, it can actually be a combination of 0 and 1. I think of it like this spinning donut. And this is called superposition. So now you see both a combination of 0 and 1. And the quantum bit can do this, whereas a classical bit cannot. And so let's see a little bit of the power of quantum computing. So let's say you have a donut box, you open it up, and inside you see two donuts. Either you see plain, or you see plain frosted, or you see frosted plain, or you see frosted frosted. You can only see one particular combination. But now, if this were a quantum box and we had quantum bits inside, we'd actually see these two quantum bits, quantum donuts, spinning. And essentially now we see all of these combinations simultaneously. And that's sort of how the quantum computer can work, is because it can now have these quantum bits in superposition, it can see all of these process these combinations simultaneously. So to understand a little bit of the power of quantum bits, let's say you had 300 qubits in superposition. How many combinations would that be equivalent to? In other words, how many classical bits would you need to represent just 300 qubits? And again, it's an actual question, so you can get out your poll. And this one, the other one was a guess, but this one you can actually mathematically do if you get it. Yeah. So I'll give you guys a few seconds for that as well. So 300 qubits in superposition. How many combinations? You guys a few seconds. Let's see if we have some responses. Okay, great. We have responses. All right. So you guys are correct. It's 10 to the power of 90. And so the reason is because you have 2 to the power of how many qubits combinations you have. So it would be 2 to the power of 300, which is roughly 10 to the power of 90. So this is 10 to the power of 90. So you need 10 to the power of 90 classical bits to represent 300 qubits. And this number, 10 to the power of 90, is so large, it's larger than the number of estimated atoms in the universe. So that's the power of superposition. So we have the quantum bit, but how does a quantum computer actually work? How do you sort of manipulate these quantum bits? Well, we use something called quantum gates. So on a classical computer, you have logic gates. So for example, if your bit is 0, you put it through the NOT gate and it ends up being 1. And this is sort of the building block of the computer. You have these logic gates, and from there you can build modules like addition and multiplication. Then you build your circuit chip, and you have your computer. Very simplified. But quantum gates, in quantum computers, we have something very simple, similar, called quantum gates. And so these change how our qubits behave. So for example, we have something called the NOT gate, which is equivalent to the logic NOT gate, where it's 0, and then you put it through the NOT gate, and then it ends up flipping it to 1. And this is sort of classical, so there's nothing in particular special about this. But we have special gates. So for example, we have something called the Hadamard gate. So it's 0, we put it through the gate, and then actually it ends up in superposition, like this. And there are other quantum gates that we have that basically manipulate the qubit in different ways, maybe like spinning this way or whatever, and it manipulates it in different ways, and that's how we sort of compute with a quantum computer. So to give an analogy, let's say you're baking a cake, right? You might use a recipe, and the recipe tells you a set of instructions on how to use the tools you have, such as a whisk, to change the ingredients, such as eggs, so that you end up getting your cake, the result. Well, a quantum algorithm, as I talked about, is a set of instructions like the recipe. So a quantum algorithm tells you how to use the tools you have, and those are the quantum gates, such as the Hadamard gate I just showed. How to use the tools you have to change the ingredients, which are the qubits, so that you end up getting the desired solution that you want, such as, this is supposed to say the blue ball that you're searching for in this problem. So this is how sort of overall a quantum computer works. So finally, all of this wouldn't be very useful if humans can interact with quantum computers and program them. So lastly, you can actually program a quantum computer. And it's kind of cool because computers used to only be accessible to scientists, like just normal computers. But there was a big shift in the 1970s, and that's when computers became available for anyone to use in their own home. And that really transforms the classical computer industry because people played around with them, they programmed them, and then that really let the field take off. Well, it's a similar way. People think that quantum computers are only accessible to scientists, but that's actually not true. Anyone can actually program and use a quantum computer. And you do that using the quantum gates that I showed you. So here's a little example of how you would use it. So this is something called the IBM Quantum Experience. But basically, you can go Google this online, and they give you this interface. And you see up here, these are the quantum gates. So these are all the tools you have to like manipulate the qubits. And then basically, you just kind of drag and drop what gates you want. So for example, if you want Hadamard gate, you drop it onto this first line, and then you can actually click run, and it will run on a real quantum computer. And then in this case, because it's the Hadamard gate, it puts our computer into superposition. So it would tell us that our qubit in superposition. It would tell us that our qubit is now in superposition. And anyone can do that online. And you can actually do real cool things with quantum computers nowadays. So, for example, you can play quantum chess. Google have created a whole quantum chess game, and there's even quantum chess tournaments if you want to look online. And it's like it's more complicated than chess itself. So it's quite fun to try and understand. But there's also machine learning. So I mentioned you can actually run machine learning algorithms, like you can classify different digits, handwritten digits, if you wanted to on a quantum computer. And you can do optimization problems, so for example, finding the optimal path for a bus. So there are actually lots of things that you can do on real quantum computers nowadays. But I should note that the quantum computers we have are limited. There's a small number of these qubits, so you can't do really large, machine learning algorithms, and you have to do it on a small amount of data. So that's sort of where we are right now. And sort of the goal with doing anything on the quantum computer is to use the quantum effects, such as superposition, to solve problems in new ways that could lead to faster and better results. And so this is sort of the power of quantum computing and why it is able to do what it can do. So lastly, let's take a look maybe at a bigger, at the field as a whole and look at the progress of quantum computing and how much progress we've made. So first of all, the hardware. So how do you actually physically build a quantum computer? Well, how do you build a normal computer? Well, we use transistors, which basically act as zeros and ones. They block and allow the flow of electrons to act as zeros and ones. And transistors took off, and that's why we have computers everywhere. But actually, it's funny because people used to use vacuum tubes. People used to use vacuum tubes, and it turns out that transistors were more scalable, easier to use, and so that's why we use transistors today. But I give this analogy to show that there's actually different ways of building a computer. There's different ways of building a quantum computer. So, for example, you can use superconductors, which I showed at the beginning of this talk. You can use trapped ions, which are atoms with a net electric charge confined in a space. You can use photons, which is basically light. And you can even use diamonds. And so I have some friends working on diamond quantum computing, and they're very casual, like, oh yeah, if you want some diamonds, just let us know. So as you can see, there's many different ways of actually building a quantum computer. And at the moment, we don't have a clear winner, we don't have a clear transistor, but people are sort of experimenting with these ways. And I'd say the most popular way is superconductors. So for example, Google and IBM, they're all building superconducting quantum computers. And these are the ones, if you wanted to access online a real quantum computer, that's typically the one you'd use. But there are startups working on all of these different methods. So to actually give you an idea of what this quantum computer looks like, I visited the Leak Lab at the University of Oxford here, and they actually have a spin-out company called Oxford Quantum Circuits, where they're building quantum computers for applications. So here's a video of me visiting the lab. So here I. Oh no, that didn't work. Okay, let's go back. Okay, it seems to have stopped.
Just a brief illustration of why we can't quantum compute.
Yeah, exactly. Maybe I can just play it from here. Okay, it's not as big, unfortunately, but okay. Well, yeah, here I think. Okay. I think it keeps. Yeah. Well, I'll just keep playing it. You can see step by step, and that's it. Yeah, so here we can see we have, I don't know why it's doing this, but here we have the quantum computer. So this is actually, this is like a fridge, and basically this is used to cool down the quantum bits. So at the beginning of this talk, I showed that you needed to cool down the superconductor in order for it to work. Well, it's similar here because you need to cool down the quantum bits in order for them to have their superconducting properties. And so this is actually a look at the inside of this fridge. Yeah, this is very weird, but yeah, and so here is just like the liquid nitrogen that you would use. And in my hand, I'm actually holding 4 real qubits. And you can even see the qubits with your naked eye, if you look closely enough. So here we have these 4 qubits. And if you look closely enough, they even have the shape of a donut. So yeah, that was me overlaying it. But yeah, and you can actually have different flavors of qubits, so you can have different shapes. There's not only one shape. But these qubits, they're basically placed at the bottom of the fridge, and when you run something on the quantum computer, so for example on the IBM Quantum Experience, what's actually happening is it's sending the instructions, the gates you have, and it's sending them to the quantum computer through the cloud, and then it will sort of go, the instructions will be sent to the quantum computer, and then they will actually apply the gates to the qubits. So for example, they will put it into superposition, and then you'll actually measure the result, and it will tell you what the result is. So yeah, so that's it. That was an interesting video. Okay, so yeah, so now I showed you 4 qubits, but I want you to estimate how many physical quantum bits we have now on the largest quantum computer that there is for superconductor technology. So you can again vote at this website.
Can you clarify the question? Sorry, how many physical quantum bits do we have in existence?
Yes. Yeah, so what is the largest quantum computer in terms of number of qubits?
Oh, okay.
Yeah, but for this particular technology, superconductor. Okay, so let's see, we got some results. Okay, great. Okay, you guys are quite optimistic. Again. So the correct answer is around 50 to 100 qubits. And this, maybe if you did put 1,000, some people put 1,000 because there are other quantum computing technologies. Maybe you've heard of D-Wave, and they claim to have thousands of qubits, but it's not equivalent to this qubit. So that's a little caveat, which maybe. But yeah, if you're like, oh, I just read 1,000 in the news, but it's a different type of technology. So around now we have about 50 to 100 physical qubits of it, especially with the superconducting technology. And so we've made a lot of progress, as you can see, and it's actually quite incredible that we can even have around 50 to 100 qubits, because there's a lot of challenges. So for example, let's go back to the spinning donut. Here, when it's spinning, it actually eventually stops spinning. And this is an analogy for quantum bits, because when they're in superposition, they actually eventually lose their superposition. And it's hard for them to maintain their quantum effects for a long time. And it's even harder when you have multiple qubits spinning or in superposition. And it's a real challenge to control these qubits because they're very fragile. And to give you an idea of how difficult it is, this is sort of a graph. I went to a Google talk on quantum computing, and they showed me this graph. And the point is, you don't need to know all the details, but this is sort of the processes to control 2 qubits. So 1 dot equals 1 physics experiment. And this was the guy's PhD that was presenting this talk. So as a PhD student, I don't know if that's encouraging or discouraging. But as you can see, this is just to control 2 qubits. So it's crazy. There's a lot of steps involved just to control qubits. So we've taken a look at the hardware, but now let's take a look at another significant step or a milestone in the field of quantum computing, and that is quantum supremacy. And you may have heard about this in the news. But this was quite big in 2019, but basically Google wanted to sort of do a race between a supercomputer and a quantum computer. Because before that point, anything you could do on a quantum computer, you could actually do on a classical supercomputer, because you could just kind of simulate it. But they wanted to show that for one particular problem, you could actually run something on the quantum computer faster than the world's best supercomputer. So they took this problem, it's a very specific mathematical problem. They They ran it on the quantum computer, and it took just 200 seconds. And they estimated how long would this take on a supercomputer. And they said 10,000 years. And so this is an actual problem that they ran on a real quantum computer. So as you can see, it speeds up this problem significantly. But the only issue is that this is for a very specific mathematical problem, and it doesn't have real-world applications yet. So the next goal in quantum computing is the next big opportunity, and this is something called quantum advantage. So this is basically where we want to take this quantum supremacy experiment and do it for a real-world problem, for a problem that, like, would take 10,000 years on a supercomputer that we practically can't do. And if we could do it on a quantum computer, we could do that problem. So this is called quantum advantage, and this is sort of what a lot of companies, a lot of researchers are working towards right now. And to give you an idea of sort of why we think we can get there eventually is because the hardware providers, they want to build more resources, right? They want to build quantum computers with more qubits, whereas people who are developing algorithms, they want to actually use fewer resources. They want to design algorithms that use fewer qubits. And so eventually, hopefully, we converge at a point where we can then get these quantum applications. And so that's sort of the thing that's happening right now. And so, as I mentioned, there's a lot of companies, a lot of people working on this. So, for example, we have public companies. Some are just doing software. Some are doing hardware and software. We have IBM, Google, Honeywell. We have private companies. These are startups. So, for example, we have Oxford Quantum Circuits, obviously here. We have Xanadu, based in Canada, PsiQuantum in the US. And there's, of course, universities such as Harvard, Oxford, and other universities around the world working on this. So as you can see, this is sort of an overview of what we've talked about. We talked about the potential applications, searching and factoring, understanding nature and machine learning, the power of the quantum computer, the quantum bit, quantum gates, and quantum programming, and finally the progress we've made in the hardware, the quantum supremacy milestone, and the opportunity. So as people build new applications and we unlock the power of quantum computing, and we build a quantum ecosystem to contribute to the progress of this field, it's only a matter of time until quantum computing turns our world upside down. Yeah.